So in 3.5, we're talking about solving polynomial equations and inequalities. And the truth is we've already really learned how to do this, at least for quadratics. We know that we can take the factors, I'm just going to call them p and q for now, of a quadratic equation, set it equal to 0, and that tells us that our factors are p and q. And then we've learned from the fundamental theorem of algebra that I can take a polynomial of degree n and split it up into n factors. So if the degree of f is n, then there are n factors, which means there are n zeros. And we've learned from synthetic division and the rational zero test how to do all of this, so there's nothing really to teach here because we really already know how to do it. We're just extending our knowledge out to larger examples. So of course for my rational zero test for this example here, I'm going to start by finding my factors of the constant, my factors of the leading coefficient, and I just kind of need to start trying things, right? So I'll give, well, 1's an easy enough thing to try. Of course, if 1 doesn't work, I can try things like -1, positive -2, and so on. -1, -6. But of course, in this case, 1 does work. So again, I like to keep track of my work as I do it on the side. So I'm left with x squared minus x plus 6. And if you remember from fundamental theorem of algebra, we do this algorithm with division until I get to something quadratic because I know how to factor a quadratic. So this x squared minus x minus 6 is going to factor into x minus 3 and x plus 2. Well, and just like we learned from quadratics, I can take these three factors, isolate them, set them equal to 0, I'm going to get 1, 3, and -2 as my roots. So my solutions to this equation are 1, 3, and -2. We can use the same logic of extending out our prior knowledge when we talk about inequalities. We can still start by treating this like an equation, just like we did with quadratic inequalities, right? Because we want to find the boundaries for our sign chart. Well, I'm not going to redo the problem because we just did it up here. I intentionally picked the same problem. I know that I've got 1, 3, and -2. And just as we did with quadratics, this is going to turn into a sign chart. So I have -2, 1, and 3, and I want to test values that fall between my bounds here. So maybe we'll test -5, test 0, we'll test 2, we'll test 5. Well, it's going to be easier to use the factored version, so let me actually grab that from a different color here. Let me grab that from above, so -3 plus 2. So if I plug in -5, I'm going to get -6 times -8 times -3. So 3 negatives all multiplied together give me a negative number. If I plug in 0, I'm going to get a positive result, right? -1 times -3 is +3 times +2 is +6. If I plug in 2, so I get 1 times -1 times +4, so I'm going to get a negative result. If I plug in 5, I'm going to have +4, +2, +7, so I'm going to get a positive result there. And I want the values that are greater than or equal to 0. Should be a little bit smaller. So, well, that tells me that I want positive values, or 0. So I have positive results when I'm between -2 and 1, and from -3 to infinity. And this would be my solution set for the inequality. It's worth noting that the sign charts will not always alternate. That happens to happen here, that happens to happen with quadratics, but it does not always have to alternate positive and negative. So do not take that for granted. Don't just find one and assume that it's going to stay the same way, because it's not. That's not always true. I can come up with functions that do not have alternating signs in their sign chart. I guess what's really new about this section is trying to work in the graphing calculator just a little bit here. So I'll show it on my calculator in just a minute, but I want to set it up a little bit first. When we're using our GDC to solve an equation, or if I think about the graph of any function, and I don't know if this is really the graph of the function here, I'm just going to sketch a cubic function, something like this, right? Well, my solutions are where the function is equal to 0. So the function is equal to 0 when we hit the x-axis here, and you can kind of see these 3 points. I'm just going to call it A, B, and C for now, just so you can see them. And of course, we call these zeros. And on our calculator, especially if you have one of the TI-83 or 84s, we're going to press second, and then you're going to see, well, it's the trace button, but by pressing second, it brings us to the calculate menu, the calc menu, and then I believe it's option number 2, which allows us to find a 0. I'll walk you through how that process is going to work. So I'm back with my kind of MacGyvered camera stand so that way I can film my calculator screen. But if I want to do some equation solving with my calculator, I can. I'm just going to start by graphing the function. I'm going to start by entering the function in. So the function from the video was x cubed minus 7x plus 6. And whoa, that's not right. Let's try this again. X cubed minus 7x. Try this one more time. X cubed minus 7x plus 6. And I'm being careful to use this xt theta n key as my variable. In my experience, that seems to be the only way that the calculator will really cooperate with entering a variable in. But once I have it put in, I'm just going to press graph. I like to just check and make sure all my zeros are visible, and they are. So even though I can't really see the whole function, right, you can see like the top of the function here, this local maximum is not visible. That's okay, because I want to find the zeros, and I can kind of see them right here. So as I said before, I'm going to press second, and then calc, also trace, but because I have the second function on, I can press calc, and I want to find the 0. And now I've got this left bound, right? So this is going to say, well, we can kind of see pretty clearly that right about here is one of my zeros. And with left and right bound, we're kind of telling the calculator, okay, zoom in around this 0 and then tell me the point where the graph hits the x-axis between these two values that I give you. So we're going to set, in this case, because the graph is moving from lower to higher, right, from negative to positive, my left bound is actually going to wind up below, right? Because if I move along the x-axis from left to right, my function's increasing. So left bound and my right bound, I just want to make sure I'm somewhat above the x-axis here. Don't guess, don't waste your time guessing, just press enter. And I have a 0. I have x equals -3. And I'm going to repeat this process for each of the zeros that I have. So I'm going to go ahead and do my left bound for this next 0 right about here. And you notice this time that my left bound is above the function, and that's because, again, as I moved from left to right across the function, left bound is looking before I hit the 0, and that would be, in this case, above. So enter there. Right bound, again, make sure I'm below the x-axis here. Don't guess. And I got another 0 at 1. I'm going to do this one more time. Get my last 0. Negative. That one that's positive. Don't guess. And I get another one at 2. So that's how you would find the zeros using your calculator. So with inequalities, we see something similar happen. And to make it easier, I'm just going to start by defining these as f of x and g of x. Just so this way we have some shorthand here. And we have two methods. The first method is going to be to find where f of x and g of x are equal, and then kind of visually inspect the graph for where f of x is less than g of x. And I guess you could also do this kind of by a sign chart, sort of, kind of, if you wanted to. But that's kind of method one. Method two would be first to find the function that is kind of this set equal to 0. So I would start by setting this equal to 0, and then treat it like an equation, right? So I want to find where f of x minus g of x is equal to 0. Right? So we would find the zeros kind of just like we would doing this by hand, right? Find the zeros. Again, we can visually inspect the graph or create a sign chart if you prefer to stay organized. I prefer this second method a lot more than I do the first method, because depending on the graph that you get, or the functions that you're going to have to deal with, you tend to get some very close intersections that can be hard to find, right? If I'm trying to find where f and g are equal, I'm trying to find the intersection point. Oops. Whereas here, I'm going to find the zeros just like I did above with the equation. So I like part two because it's streamlined, right? It's the same method that we've been doing. Nothing is different. I will stick with just the second method in this video, but you're welcome to kind of go back and learn the first method if you so choose. I'm going to show the method that I think is a little bit more simple, and hopefully connects everything a little bit better. So in order to do this on my calculator, I again need to start by graphing this function. And if we're following the second method, then I need to find f of x minus g of x first. So this is something that we would do by hand. I would have moved the 2x to the 7th and the plus 1 over, so I'd have minus 2x to the 7th minus 1, and I'm going to just graph that function. Okay, and we can see that all of my zeros are pretty close together, so I'm actually going to expand this window. So I'm going to press window. I just want to stretch out my y-axis quite a bit, so let's try maybe from -3 to 3 and see if this makes it a little bit easier to spot my zeros. Yeah, that's going to make it a little more accurate and a little easier for us to see. So just like before, I'm going to press second calc 0. I want to be above. Whoa. Above and below. So I got 1 at about -0.496. Do this again, right? Left bound below in this case. Above. 1 at about 0.504. And do it one more time. About 1.10, right, with our 3 significant figures. So out of our 3 functions that are zeros there, right, there's about negative point, what we said negative, we'll call it -0.5 for the sake of timing. R1 over here and R1 over there. I want to find where this function, right, my difference of the functions, is less than 0. Well, it's less than 0 when the graph is negative, so in this region here and in this region here. So we would have between these two zeros, I think it was like roughly -0.5 and roughly positive 0.5, right? With parentheses, because we're not including those points. And then from 1.10 all the way to infinity, because well, the whole graph is negative at this point. So it really just builds on everything we've already talked about, and that's why I like this method a lot better than the intersection method, because it already builds on our prior knowledge in a much clearer, simpler way. Really quickly, one last thing. If you're the type that still wants to organize this on a sign chart, you can see that I've done that down here, right? I've taken my 3 zeros, I've listed them on the number line, and I've already kind of done this just by visual inspection of the graph, right? Just by looking at the graph, which intervals produce positive function values and which produce negative function values. And well, since I'm curious in this case just about the negative function values, because I want less than 0, then of course my solution set, my interval, would be given as follows, just like this.